and welcome to a proof on differentiation. Calm the hell down, it's not even that bad. Why should you even care? Don't listen to some random big mouth hippie guy you saw on the internet. Why don't you ask one of the greatest mathematicians of our time? That's right, Kendrick Lamar.
Everything in life subject to change. Change whip, change grind, change clothes, change opinions right before I change my mind.
Let's say we have a function, y is equal to f of x, where f of x can be absolutely fucking anything. As you may already know, the differentiation formula is dy over dx, where d means tiny change. In a moment, I'm going to get into why d has to be tiny, but can we just talk about something right here for just a moment? Isaac Newton, one of the inventors of calculus, chose the letter D of all letters to mean tiny change. Better luck with ladies in the afterlife, bro. It's very important to remember, guys, that when it comes to maths, you can't just draw a curve with your hand and expect that to mean something mathematically. When you see a curve, that's because the points between them, where there are straight lines between them, the spaces between those points are so tiny that you can't even see those straight lines, and to the naked eye, it just appears like a curve. So, let's say we have a curve here, right? It looks something like this. Okay, that's our golden, or should I say purple standard. Let's say we actually had a step size of 21 between our points. Let's see what that would look like. Yep, let's give that a shot. Alright, step size of 21. So we have a step size of 0 to 21. Get that shit out of my face. What the fuck is that? That's not even a curve. Look at all that lost accuracy. Man, this is giving me Vietnam flashbacks. I don't even want to look at that anymore. So let's say we have step sizes of 13.5. No, pardon me. 10.5. Okay. 0 to 10.5 and 10.5 to 21. Okay, that actually looks a little bit more like it. Okay, that's not bad. Let's go off that. Now let's say we have step sizes of 5.25. Alright, 0 to 5.25, 5.25 to 10.5, 10.5 to 15.75, and 15.75 to 21. See? Look at that. That actually looks more like the curve we're supposed to have as you decrease the step sizes. That's what we want. So guys, when I said step sizes, I meant step sizes in x, where step size in x will mean that y will follow accordingly. So which means for the purple, we pretty much had step sizes of dx. Which, like I said, is a tiny change. I ain't drawing that shit out, I'm just gonna draw dots. That you guys get the picture. At least I hope you do. Nah, I'm kidding, of course you guys do. You guys are the best. Yeah. Like I said before, guys, any curve you can imagine is actually made of tiny straight lines which change gradually. So if we were to zoom in onto this guy right here, here's what we pretty much get. Yep, we just zoom in. We would literally get a straight line if we zoomed in deep enough. Straight up. Looks something like that, pretty much. So, we don't really know any specific points, but we can just call them whatever. We're going to call it over here, pardon me, x, and these are our coordinates, x, f of x. Nice and simple, right? Like I said like a million times, this might as well be a drinking game. Our step size is dx, so if we shimmy along here, we would have x plus dx. So ultimately what we have up here is x plus dx, and f of whatever our x is, so we have f of x plus dx. No trickery, no magic, it's just whatever our x coordinate is, we stick that in the f bracket. Following through, no magic, no sorcery, no trickery, it ain't even that big. I'm telling you guys, differentiation ain't shit.